In this video, we're going to talk about multivariate functions and how to find local maximum, minimum, saddle points. Let's start from the beginning. Our function f(x) of y, for the purpose of this video, let's just call it for now, let's call it zx and zy, and you'll see in a minute. So if we have zx, zy, and the result is less than zx y squared, you'll find in a minute what this means. This is an inflection point. On the other hand, if these 2 points zx are both positive, which is in the case at the top, so if they are both positive and they are greater than zx y squared, this is a local minimum. Because what this means is that the function is pointing like this, so it's pointing upwards. This is the second derivative that we're talking about here, and we have this kind of restraint here. So this is not that important for now, just for you to know the conclusions. This is the most important point at this point. This is the key part at this point. So both of them are positive and they are greater than this one. It's a local minimum. On the other hand, if we have zx and zy and both are negative and greater than zxy squared, this is a local maximum. Because what this means is that both of them are pointing downwards, so essentially if you look at this in the graph, this is a maximum. Okay? And the last one, if you have zx and zy, and both of them have different signs, it really doesn't matter if one is positive or the other one is negative. The key here is that both are different and that they are greater than zx y squared. This means that our point is a saddle point. Okay? So these are some of the definitions, because in the end you'll need to know what to conclude from the study of the function. So again, fxy, we can address it as z for now, and then we have a couple of conclusions. So the first one is both are positive or have the same sign, but it's the result when they are both multiplied is less than this constraint. So this is an inflection point. If both of them have the same sign, so if it's positive and greater than the constraint, is a local minimum, because the function is pointing upward. So in a graph, we have something like this. If you have the other way around, so when both of them are negative and greater than the constraint, this is a local maximum. Again, because the function is pointing downwards, remember this is a second derivative, it's telling us if the function is pointing upwards or downwards. The last case, if both of them have different signs. So if that's the case, different signs. So if that's the case and they are greater than the constraint, this is a saddle point. Okay? Now that we have this definition, let's talk about another definition that is important to know. Because you'll find that when you're doing these exercises, you'll get right away doing the exercise, and then they throw something like a curveball and you don't know how to deal with it. So the next part to solving this is dealing with cross partials. And this is how we solve this. So cross partials is you will have derivatives in terms of x, you will have derivatives in terms of y, and we will have derivatives in terms of x, y. And this is what we are talking about here. And these are called cross partials. So let's solve some examples. So let's say we have x squared, y to the third power. The cross partial of this is 6xy squared. All we are doing here is doing both derivatives at the same time. That's essentially what we are doing. So you have this one comes downwards, this one comes downwards as well, and we remove one from both of these. So we have 6, which is a product of 2 with 3. X, we removed 1, so it was squared, now it's just 1. And y was 3, now it's 2. Okay, so let's do another one. So let's say now we have the other way around. So we have x to the third power and we have y squared. Again, it's the same thing. So both of them come down. So it's 6. And now we remove one from each. So x to the third power is x squared. and y squared is x1. Okay, let's do another one. So let's say now we have this one, 3xy. So both of these have the same power, so they come down. So this is 1 times 3, and because these we remove them from this exponent, it becomes 0, and anything to the 0 power is just 1. So our derivative is 3. Okay, let's do another one. So let's say now we have 8x squared y minus 11x y to the third power. What's the cross partial of this one? Well, we start by doing the first one. Again, this is the same thing, so this one comes down and multiplies what we have here, and then we remove 1 from both of these. So it becomes 16, x it was 2, now it's 1, and y it was 1, now it's 0, and anything to the 0 power, it's 1. And the second one, we're going to do the same thing. So this is 11 times 3, that's 33. 1, it's to the first power, it becomes 0, so it's 1. And the second one, y, it was to the third power, and now it's y squared. So our solution, let's just clean this up a little bit. So it's 16x minus 33 y squared. This is our solution, okay? So let's do another one. So let's say now we have this one. We have 8x minus 4y to the fifth power. What's the partial of this one? This is why I want to do this exercise, because like I said, they throw you a couple of curveballs, and if you don't have enough practice solving a couple of these key points, you'll get into trouble. So the way for us to solve this is understanding that we have both two things. We have x and y. So instead of this coming down just once, it's going to come down twice because we have 2 here. Okay? So let's say we were doing the derivative of in terms of x, it would be just coming down once. But because we have y, we're going to do this twice. Okay? So the first step again, 5 comes down, right? We have 8x minus 4y. And we are solving this in terms of x. So this is 8 that comes outside. Okay? So for now we have 40. And we are now multiplying also by the derivative of this one, which is minus 4. Okay? And because we multiplied by this one, that also means that this one comes down again. So we have 4 here, and this becomes 3. So what we have here, let me just clean this a bit. We have 5 times 8 times 4 times minus 4 times 8x minus 4y, and this to the third power. And this is 40 times 4 minus 4, 8x minus 4y to the third power. So this is, what is this? So it's this 160 times minus 4, 8x minus 4y to the third power. So this is minus 640, 8x minus 4y to the third power. Let's look at this one again. So what is it that we did here? So we had 8x and we had 4y, and this is a cross partial. So what this means is that we are doing the derivative of x and y. Okay? So when we do that, essentially we are doing this 2 times. So the first time we got the 5 down, and we did the derivative of this one, which is 8. And we also did the derivative of this one, which is minus 4. And we got the minus 4 down. And then because we addressed the derivative of this one, we need to remove another one from this one. So this becomes 3. Okay? So in the end, you do the cross multiplication, and we get minus 640. Alright, with that out of the way, let's solve some exercises now. So let's say we have this function. We have x of y. We have this 2y to the third power minus x to the third power plus 147x minus 54y plus 12. So we need to study this function. So the first step that we are doing, the first thing we do is find the derivative of the function. And the reason why is that, let's say we have something like this, we are interested in knowing the points that the derivative is 0, and it can be this case, it could be this case, or it could be this case. So it's something like this, right? And we find these by first knowing whether the derivative is equal to 0. This is how we find these points. And then, because we don't know the direction, if it's going down, if it's going up, or if it's just changing from one to the other one, this is what we'll be accomplishing with the second derivative. But for now, the first point is finding the first derivative. So the way for us to do this, and I find it's much easier to do it in gradient form, it's essentially this triangle with call it the first derivative and x, y. You'll have two things. You have the x part and you have the y part. So the x part here, this is nothing. This is minus 3x squared. And then what do we have here? We have just one element, which is 147. So plus 147. This is the first element. And now we're going to do the same thing, but for y. So we have this one. So it's 6y squared. This one we have nothing. This one we have nothing. And this one we have minus 54. So now we have our first derivative. The second point is finding what's called the critical point. We're interested in finding, like in the graph, the points where this stuff is happening, right? We don't know the point, and this is what we're doing here. So we found the first derivative, and now we're going to address it to find the critical point. So the way for us to do that is using both these two terms. So we're going to do that right now. So it's minus 3x squared plus 147. That is equal to 0. And the second one, this one, so it's xy squared minus 54 is equal to 0. So for us to solve this, this is negative, so you can get this one to this other side to get it positive, and divide the whole thing by 3. So we get x squared is equal to 147 divided by 3 plus or minus. So this is the first one. The second one is the same thing, so we have xy squared, we get this one that is negative to the other side, gets positive, and divided by 6. So we have y squared is equal to plus or minus 54 divided by 6 square root of this. So this gives us x is equal to plus or minus 7, and y is equal to plus or minus 3. Okay? So this is what we have for now. Now the second point is now figuring out with these points if this is happening, or this is happening. So the next step is finding the second derivative. So let's do that. So the second derivative, x, y, so that's equal to minus 6x, then 12y. So this is how we're going to solve this right now. I'll write the points here for you so you can see those. So you have minus 7 minus 3. We have minus 7 and plus 3. All we're doing is finding the combinations of the points that we have, because it's plus or minus for both. So minus 7 with minus 3, minus 7 with plus 3. Same thing with the plus version. So 7 with minus 3, and then 7 with plus 3. Right, so we have 1, 2, 3, 4 points. So the way for us to use the second derivative with these 2 points is finding out how we can relate with the function. Let me show you. So now we have minus 6x, which is the point here, and we need to use the 7 here to find what's the value that we get from it. So we get all the points in front, so it's minus 7, minus 3, minus 7, 3, then we have 7 minus 3, and then we have 7 plus 3. And we're going to do the same thing for y. Let me just change colors here. So for y, it's the same thing. So we have 12y, and then we have minus 7 minus 3, same thing. You'll see in a minute why I'm doing things like this. Minus 7, 3, 7 minus 3, and then 7, 3. So I'm separating this for you to see, because we'll need to substitute it back here to figuring out the point. Minus 7 times minus 6, that's 42, and that is greater than 0. Minus 7 times minus 6, again, is 42, it's greater than 0. these two ones are negative, so it's minus 42, it's less than 0. Same thing for this one, so less than 0. And for these two, let's do the same thing here. And for these two, now we're going to use the y part. So 12 times minus 3, that's minus 36, that's less than 0. The second one is positive. This one is negative. And this one is positive, so 36 is greater than 0. And now what we're doing here, we're going to do a second table here. Let me just separate this. And now what we have here is what I call a sign study. So the way for us to relate, we'll need to relate this one with this one, this one with this one, and so on. So let's do that. So this first one and this first one, signs are different. Because if you look at it, 42, right, is positive, and this one is negative. So these two are different. Different and different. For these two, the next second pair, so this one is positive, and this one is positive. So the sign is the same. Same. For the third pair, the sign is the same. Minus 42, minus 36. So the signs are the same. So same again. Same and same. And for the other one, this one is negative and this one is positive. So the signs are different. Different and different. Okay, now that we have all this stuff, let's use it in order to make our conclusions. So minus 7 and minus 3, this one, so this pair, we have different signs. And the other one we have right here, so it's 7 and 3. We also have different signs. So these ones are saddle points. The other ones, these have the same signs, so we'll need to find if they are maximums or minimums. So for the next one, we have minus 7 and 3. This one has a positive sign here, and we have a positive sign here. So both of these are positive, the derivative I mean. So this means that it's pointing upward. So what we do is, we need to multiply what we have found. So from minus 7 and 3, so it's this one, we have 42, and we have 36. So we multiply these, so 42 times 36, that is equal to 1,512, and that is greater than 0. Remember, the 0 comes from the partial derivative of an element that has x and y, but in our specific function we don't have it. So this means that this condition applies. So this function has a minimum, which is given by this point. So this is a local minimum. And for the other one, for 7 and minus 3, so again we're doing the same thing. So both of these, when you look at the graph, so both of these have the same sign, so this is negative, and this one is also negative. So this means that this is pointing downwards, and we need to find if it's in fact a local maximum. So in order for us to do that, we're going to do the same thing. So you're going to find the relationship between the multiplication of both these two values. So let's just do that. So again, it's minus 42 times minus 36. We're going to get the same value, so 1,512, and that is greater than 0. So this is in fact a local maximum. What about this one? So let's say now we have x of y, and this is 60x plus 34y minus 4xy minus 6x squared minus 3y squared plus 5. Again, same procedure. So first derivative in terms of x and y, find the gradient. So this is 60 minus 4y minus 12x, and the second one in terms of y is 34 minus 4x minus 6y. So now we're going to find the point. So the critical points are, so we have 60 minus 4y minus 12x equals to 0. The second one is 34 minus 4x minus xy equals 0. So our function, you're going to get 15, just dividing things to get this simpler, minus y minus 3x equals 0. And the second one, 34 minus 4x minus 6, and then we're just going to substitute the 15 minus 3x. So we have 15 minus 3x equals 0. So let's continue. So now we have y is equal to 15 minus 3 times 4. This one is 34 minus 4x minus 90 plus 18x, it's equal to 0. So this is y is 15 minus 12, and this one 14x, it's equal to 90 minus 34. So if you keep working on this, we're gonna get that this is y is equal to 3 and x is equal to 56 divided by 14. So y is equal to 3, x is equal to 4. So now the step is to find the second derivative. So x, y, we can keep going what we did from the first one. So we get minus 12 and minus 6. The first step is seeing that minus 12 is less than 0 and minus 6 is also less than 0. And we also find the cross partial derivative of x and y. And from our expression we have minus 4xy, so this is minus 4. And minus 4 to the squared is 16. So what we do here is use the elements that we have from here, and we are going to compare with this one. So we have minus 12 times minus 6, that's 72, and 72 is greater than 16. So coming back to our definitions, both signs are the same. They are negative, so the function is pointing downwards, and the result is greater than the square of this one, which is 16. So our function at the point 4, 3 is a local max. What about this one? So now we have fxy, and this is 48y minus 3x squared minus 6xy minus 2y squared plus 72x. So again, first step is finding the first derivative, and this is minus 6x minus 6y plus 72, and then for the second one, in terms of y, it's minus 6x minus 4y. So now the next step is finding the critical point. So just use the expressions that we found here. So minus 6x minus 6y plus 72 is equal to 0. And the second one, so it's minus 6 minus 4y plus 48 is equal to 0. So now that we have this here, we just need to simplify it in order to get y and x. So minus x minus y plus 12 is equal to 0. 6x is equal to minus 4y plus 48. So we get x is equal to 12 minus y, and 6x is equal to 48 minus 4y. So x is equal to 12 minus 12. In our second one, so we can substitute the elements. So 12 minus y is equal to 48 minus 4y. So x is equal to 0. This one we have 72 minus 6y minus 48 plus 4y is equal to 0. So 2y is equal to 24. So x is equal to 0 and y is equal to 12. So our second derivative is minus 6 and minus 4. So from the expression to find the partial, we had minus 6xy, so this is minus 6. And minus 6 squared is equal to 36. We notice that minus 6 is less than 0 and minus 4 is also less than 0. Both have the same sign. So we do the cross multiplication. Minus 6 times minus 4, that's equal to 24. But 24 is less than 36. So this is an inflection point. So now we have this one. We have fxy is equal to 3x squared minus xy plus 2y squared minus 4x minus 7y plus 12. Again, same thing. So first step is finding the derivative. So we use the gradient notation. So xy. Then what is it that we have here? So we have 6x minus y minus 4. And the second one we have minus x plus 4y minus 7. So let's keep going. For the critical point, which is the second step, just get the expressions out. So 6x minus y minus 4 is equal to 0. And minus x plus 4y minus 7 is equal to 0. So let's keep going and simplify this a bit. So 6x is equal to y plus 4. In this one, we have x is equal to 4y minus 7. So 6, we get the other one for here. For 4y minus 7 is equal to y plus 4. In this one, we have x is equal to 4, 2 minus 7. So let's keep going. So this one gives us 24y minus 42 minus y minus 4 is equal to 0. And this one we have x is equal to 8 minus 7. So here we have 23y is equal to 46 and this one is equal to 1. So y is equal to 2 and x is equal to 1. Let's continue. So now that we have our critical point, we find the second derivative. Again, the same thing, xy, you pick up where you left off with the expression, and in our specific case, we get 6 and 4. So now, again, it's testing this against 0. So 6 is greater than 0, and 4 is greater than 0. And the partial derivative that we find across one, in terms of minus xy, is equal to minus 1. So what we have here is 6 times 4 is greater than 1 because this squared is equal to 1. So since 24 is greater than 1, we notice that both of these have the same signs because the function is pointing upwards. So the critical point is a local minimum. So now we have fxy is equal to 5x squared minus 3y squared minus 30x plus 7y plus 4xy. The first derivative, again, same thing. I'm doing these in order for you to see that this is only about practice. The more you do this, the more you'll get better at doing the exercise. So 10x minus 30 plus 4y, and then the second one is minus 6y plus 7 plus 4x. So again, critical point, getting the expressions and equaling them to 0. So 4y equals to 0. And the second one, minus 6y plus 7 plus 4x equals to 0. So just simplifying the expressions. So 5x minus 15 plus 2y is equal to 0. So minus 15x plus 45 minus 6y is equal to 0. And this one is 15x minus 45 plus 7 plus 4x is equal to 0. So minus 6y is equal to 15x minus 45, and this one is 19x is equal to 45 minus 7. So here we have minus 6y is equal to 30 minus 45, x is equal to 38 divided by 19. So our final results are y is equal to 2.5 and x is equal to 2. Now that we have this, it's the same procedure as before. If again, same thing, xy, open this, and the results are 10 and minus 6. Again, we compare, so 10 is greater than 0, and minus 6 is less than 0, so the signs are different. So this is a critical point that has different signs, so this is a saddle point. So this one is fxy is equal to 3x3 minus 5y squared minus 225x plus 7y plus 23. Again, same thing. So first derivative. So this is 9x squared minus 225 minus 10y plus 70. So the critical point, get the expression, 9x squared minus 225 is equal to 0. And the second one, minus 10y plus 70 is equal to 0. So keep developing the expression. We get that x is equal to plus or minus 225 divided by 9. And y is equal to 7. So if you don't even need the calculator because you can do this by hand. 225 divided by 9. So the first one, so it's 2, and then you get 4, and this is 5. So this is 25. And the square root of 25 is 5. So x is equal to plus or minus 5, and y is equal to 7, right? So let's keep going. So now that we have the critical point, the second step again is finding the second derivative. That's what we're doing here right now. So the result is 18x, and the second one is minus 10. Notice that when we have these, and this is kind of a dependent variable, we're going to deal with this in the same way, but we just need to plug in the value from the critical point. What I mean is, let's say we have 18 and 10. This is already fixed, right? You don't have a way of changing this. But in our specific case, we have a variable here that takes in the value from the critical point. And our critical points, because we have x is equal to plus or minus 5, and y is equal to 7, this means that our points are minus 5 with 7, and then 5, so the positive version, with 7 as well. So this means that in this particular point that we have x here, we need to test it with both these 2 points. So let's do that. So 18x, and then we have 2 points. So we have minus 5 with 7, and then we have 5 with 7. So for our first point, when we substitute 5 with 18, that's minus 90, and that is less than 0. And for the second point, because it's positive, we have 90. So our relationships to study are minus 90 with minus 10. And the second one is 90 with minus 10. So we need to find in the expression the element where we have a cross partial. In this specific case, we don't. So this is 0. And 0 squared is 0. So all we're doing here right now is testing these to find if it's a local minimum, maximum, or saddle point. The first one, we notice that it has the same sign. We get negative 90 times negative 10, which is 900, and that is greater than 0. And because these have negative signs, they are the same, this means that the function is pointing downwards. So this is a local maximum. So minus 5 and 7 is a local maximum. And the second one, because it has different signs, so 5, 7, it's a saddle point.